Have you ever thought of a language not as a messy collection of historical rules, but as a perfectly logical machine? Well, today, we're diving into a grammar that does exactly that. It treats Old Church Slavic, a really complex ancient language, like it's a solvable algorithm, a piece of software with predictable, almost mathematical outputs.
Okay, let's just let this sink in, because this single quote is the key to everything. This grammar basically says, forget tradition, forget all the other theories. It builds its own universe with just one guiding principle: pure internal logical consistency. It's a completely self-contained system, built from the ground up, almost like a mathematical proof. So, to really get our heads around this radical approach, we're going to break it down into 4 parts. We'll look at the machine's main function, we'll examine its source code, see how it handles real-world bugs, and then finally, we'll understand the new blueprint it offers for looking at all kinds of complex systems. All right, part 1. If this grammar is a machine, what's its core program? Well, its whole purpose is to be an explicit, predictable engine for generating language. No guesswork, no ambiguity, just pure computation. This right here gets to the heart of the machine's mission. Think of it like a mathematical function. Seriously, your input is a lexeme, that's kind of like the dictionary form of a word, let's say to go, and you add a set of variables, like past tense, third person. The machine runs its algorithm, and it gives you one and only one correct output, the exact word form. It's just beautifully predictable. And this is what makes this machine-like approach so wildly different. See, traditional grammar is always looking backward, right? Tracing history. This grammar, though, it takes a snapshot. It freezes the language in a single moment and asks, what is the most logical, most mathematically efficient system that describes this exact state? It's all about optimization, not history. Okay, so let's pop the hood on this machine and see how it's built. To write an algorithm, you need fundamental units of code. And you know what? This grammar just invents its own. So the basic building block here isn't a word. It's not even a morpheme. It's something called a formative. The best way to think about it is as a string of data. It's just a sequence of sounds, a piece of formal information, and it's completely stripped of any built-in meaning. Now this is where the real genius of the approach becomes clear. By separating the unit from its meaning, the grammarian is totally free to slice up words in whatever way is most efficient for the algorithm. It's not about what a piece means, it's about how it functions inside the formal system. And here's how those formatives get organized. Every single word can be mapped to this formal schema based on where its parts go. So, for example, the word for to exit in Old Church Slavic that you see here, it breaks down perfectly into its prefix, root, and suffixes. This isn't just a word, it's a structural blueprint. It tells the machine the exact syntax for how to assemble the pieces, every single time. And here's where we get to see the program actually run. It starts with this abstract underlying string. Then, a series of explicit, recursive rules get applied. These rules are the core of the algorithm, and they transform the string in cycles until, bam, it resolves into the final pronounceable word. It's literally like watching code compile. Okay, this all sounds perfectly clean, right? A beautiful, formal system. But language isn't clean. What happens when this perfect algorithm runs into the messy, inconsistent data you find in actual 1,000-year-old manuscripts? The solution is just incredibly elegant. The grammar doesn't even try to describe the messy reality directly. Nope. Instead, it defines a canon, a mathematically perfect, idealized version of the language. This canon is what the machine is built to generate. It's the theoretical ideal, the gold standard. And this creates such a powerful way to analyze things. The machine spits out the perfect canonical form. Any form you find in a real text that's different, that gets labeled aberrant. And get this, it's not an error. It's a deviation that can be precisely described. This is how the system handles bugs without crashing. And you can see it right here in practice. So look at that first row. The manuscript has the word spelled one way, but the grammar's algorithm generates the perfect canonical form next to it. The system can then tell you the exact type of deviation, whether it's a difference in the spelling, the sound, or both. It's an incredibly precise diagnostic tool. So what's the big takeaway here? This isn't just a clever way to describe a dead language. This is a revolutionary way of thinking about any complex variable system. It's a whole new kind of blueprint. And this slide right here shows the payoff of that whole approach. By completely abandoning those traditional historical categories, things like A stems and U stems, the system creates this brand new classification. It's not based on dusty old history books. It's built from the ground up based on what is most mathematically economical and logically consistent for the system itself.
So this entire approach, it gives us a powerful new toolkit. It proves that you can model a messy, evolving human system with the rigor of a formal mathematical system. And by being super explicit about its goals and its rules, it gains the power to handle all that real-world noise without breaking. It really does bridge the gap between computational thinking and the humanities.
And this leaves us with a really fascinating final question. I mean, if it's possible to build a predictive, logical machine for a 1,000-year-old language, what other complex systems, social, economic, maybe even biological, are just out there waiting for us to discover the algorithm that makes them run?